So in today's class of mathematics, I will be teaching this is about the abstract algebra. In this I will be giving you all the definition of group, subgroup and normal subgroup. Okay. So let us start with the definition first of a group. Okay. You all can take down this abstract algebra part. Okay. Next what you'll have to do is write down group. Okay. Now let G let G be a group. Let G be a group and G comma 0. Now this is a binary operation. Okay. Oh. Now be a binary operation. So we have taken group under binary operation. Then it has satisfied the following. So it has to satisfy the following properties. Now a group. Okay. Let G be a group. Okay. What is G? G is a group. Now this G is a group and G comma O be the binary operation. This is a binary operation. Then it has to satisfy the following properties. Okay. So it has to satisfy the given following properties. Now what is first property is closure property. If A comma B belongs to group. Okay. If these two elements, I have taken two elements. These are two elements A comma B and it belongs to G. Then the addition of these two elements, okay, when I add this two element, it should also belongs to G. Is called closure law. Okay. Now this is a closure law. Property you can say. So basically what happens over here is, now there is two elements A and B, right? So and it belongs to what? G. So what I am saying is the addition of these two elements should also belong to G, and subtraction of these two element also should belong to G. It should also belong to G. Okay, also belongs to that group. Okay. So the closure law, I hope you all have understood. Next, let me move towards the associative. Okay. Now associative is what? You all can take down this. Okay. Let me rub this. Moving further towards the associativity. Now here what happens in associativity? Let me read it first to you all. This is associative law. If A comma B comma C, here three elements are there. It belongs to the group. Then what should happen is A plus B bracket plus C is equal to A plus bracket B plus C. Okay. So whatever values you take here and here, meaning it should be you should get the same answer in both the way. For example, if you take A to be 1, B to be 2 and C to be 3. So like what you all are going to do is, what is your A now? Your A is 1 plus 2, right? Plus 2 it is. Put the bracket, okay? Plus what it is, C is what? 3. Now here what you all are going to write down? 1 plus 2 plus 3. Here it will be 2 plus 3. So now 1 plus 2 is what? 3. 3 plus 3 will be 6, right? So let me rub this. So here it was 6, right? Now here let us see. Here it is what? This was plus, right? So and this was equal to sign is there over here. Okay. So 2 plus 3 is 5. 5 plus 1 will be 6. So are you all getting 6? So basically we are getting 6, right? So on both the side it is what? 6 and 6, right? So it should satisfy this associative law, closure law. Then you can all these four laws it should satisfy. Okay. Next let me take it further. Like next is the existence of identity. Okay. So when it comes to the existence of identity, if A belongs to G, then E belongs to G. If suppose A is belonging to a group, then E also belongs to the group. Okay, now A into E is equal to A is equal to E into A. Okay, so what was the identity element of E was equal to what, like, sorry, so basically it is equal to 1, right? Whatever it is. So if you put A into 1 is equal to what, you all are going to get, this will be 1 into A. So either way it will be A only. You all are going to get what? You all are going to get A only, right? So this is the existence of identity. It should also satisfy this. Okay. Now let me next it will be, I can take down all this. Okay, now next is the existence of inverse. Okay, existence of inverse will be what, sorry, existence of inverse, if A belongs to G, and then A inverse also belongs to G. Okay, it is not this. Okay, it is then A, this also should belong, A inverse should also belong to G. So here what you all do is, A into A inverse is equal to E is equal to A inverse into A. Okay, so if you solve this, what you all are going to get, A into A inverse, it will be 1, right? So if you solve this and all, this will be nothing but A raised to power of 0, okay, which is equal to 1, which is equal to, so this is nothing but this thing, which is nothing but 1. Okay, so basically what this identity element will be, what, 1. Okay, this. So are you all getting the point? You all are going to get 1 only. So 1 is nothing but what was E? E was nothing but what? E was nothing but 1, right? So existence of inverse, if A belongs to G, then A inverse also will also belong to the group. Okay, and have you seen about the abelian group? Abelian group will be giving you all what? A commutative law. Abelian group or commutative law. What about the fifth one will be like abelian or commutative. Okay. What it should satisfy? A plus B should be equal to B plus A. Okay. Or if it is giving you A into B is equal to B into A. This is a multiplication. Okay. So this is an abelian part. Okay, but it should satisfy all these 4 properties, then you can say it is a group. Now even you all have abelian or common group, commutative or abelian will be same. A plus B is equal to B plus A. Okay, next moving further, that is subgroup. Let us see what is a subgroup. Okay, now subgroup is what, let G comma 0 this, now this and this H comma 0 are two non-empty groups. Now these are the two non-empty groups. If H is a subset of G, okay, if this H is a subset of G, then this, what we have taken over here, we have taken binary operation over here, is called subgroup of this G comma O. Okay, now we have, okay, I have taken two sets over here is an example. Now this is a set of integers and this is a set of even numbers. Okay, now this the addition, okay, is a group, but E is a proper subset of I, so E is a subgroup of I. So when I can say that E is a subgroup of I, now all the elements over here, can you see it over here also? Now this is what? This is our integers, set of integers. And here this is a set of even number. So here this is a set of even numbers. Now 0 can you all see in this also. This 2 can you all see also. 4 is there, here also 4 is there. Now here also plus or minus 4 is there, right? Here also plus or minus 4, then plus or minus 5 and so on. So like this element is present here also, this element is present here in this also. Okay, but these are the set of even numbers. Since this is a set of even numbers and this is a set of integers, right? Can you all see this one in this set? No, right? That's but in the whatever elements are present in E are there in I. Okay, but whatever elements are there in I are not in this. Not every element. Like 1 is not there, 3 is not in this, right? But whatever elements you all can see like 0, 2, 4, 6 will be present in this. Okay, this goes to up to infinity, right? So what happens over here? So I see that this E is a subgroup of this I. Okay, and E is a proper subset. This is a proper subset of I. Okay, I'll turn the page, or can take down this. So what I can say is I comma plus this addition is a group, but E is a proper subset of I. So E is a subgroup of I. I have already explained you all this part, okay, with the help of the example. I can take down this, write it down. Okay, I'll take it. Let me see the normal subgroup. Normal subgroup. Okay, let G comma O is a group and N comma O is a subgroup of group G of G. Okay, then N is said to be normal subgroup of G for all G belonging to capital G when belongs to capital N. Small n belongs to capital N. Okay, G intersection G inverse belongs to N. So this is a definition of a normal subgroup. Okay, now this is also under binary operation I have taken, right? So basically you all can take down all this definition. Okay, you all can take down this also, whatever was there before normal subgroup. This is your normal subgroup. Okay, so I hope you all have understood all these definitions and you all can take down them. And thanks for watching.